Hi, my name is Yuta Han, and I will be presenting my collaboration with Hubert Ling and Jacopo Banfi at Cornell University. We present deep semantic hypothesis-based planning over uncertain point clouds, a framework for a novel uncertainty-aware hypothesis-based planner for unstructured outdoor environments. Traditional planning literature is mainly based on planning in structured indoor environments. When planning in outdoor environments, there are unique challenges which are not present in indoor environments. One of these challenges is assessing terrain safety. Existing work for outdoor environments typically focus on 3D environment structure to assess safety. However, outdoor environments cannot be safely planned in without accounting for different semantic surface types, which is the key problem our paper aims to address. Here is a deceptively simple environment. A traditional LiDAR-based planner will detect a flat ground plane and plan a path directly forwards. Unfortunately for LiDAR-based methods, outdoor environments are frequently populated by terrain surface types which are not traversable. In this example, there's a patch of muddy water in the middle of the environment, which would be hazardous to a four-wheeled robot if we chose to navigate over it. Our goal is safe navigation through unstructured outdoor environments. The key insight of our work is that it's important to reason about semantic terrain information. We'll compare our planner to a state-of-the-art outdoor planner which does not account for semantic terrain information, demonstrate that our planner selects paths with a significantly higher margin of safety. The contributions of this paper are: we identify integrating semantics as critical in path planning. We develop a method to use semantic labeling with uncertainty in path planning. We develop next best view selection to decrease uncertainty while path planning. And we demonstrate better safety in path planning in unstructured environments compared with baselines. The following is a high-level problem statement of our work. Given an initial starting location and a final location, our planner aims to find a safe path through a 3D outdoor environment. We assume there is already a non-labeled point cloud map of the environment, as we are mainly interested in navigating through different semantic terrain types in this work. Our iterative algorithm generates multiple hypotheses or possible paths and selects the safest path to take as semantic information is fused into the map. Now we present the algorithmic flow of our full pipeline. This will be a high-level overview. For more detailed methods and experimental results, please refer to our paper. From an initial starting location, we capture an image measurement of the scene. To extract meaningful information out of the image measurement, we use a deep Bayesian neural network. We use a DeepLab framework, a state-of-the-art segmentation network, to extract semantic labels. To train this network, we filtered the Cocoa Stuff dataset for images with labels of outdoor surface types. The data and pre-trained network can be accessed at our project page linked here in the red. You can also find the link in our paper. While neural networks have a reasonable level of accuracy for segmentation tasks, there are still many sources of uncertainty in outdoor scenes, which cause false positive measurements. In this picture, for example, there are shadows cast from the tree, which cause a high level of uncertainty in the network. To reason about that uncertainty, we use a Monte Carlo dropout method, which is an approximation of a Bayesian neural network. Each pixel of the image is assigned a probability vector of classes it could belong to, and uncertainties associated with those classes. The next step is to fuse the measurement into the world belief of the planner. We take the semantic labels and associated uncertainties and fuse them into the unlabeled 3D point cloud. On the right is the result of the fusion of the semantic labels and uncertainties of the initial image into the point cloud. Now that we have a map with some semantic information, although uncertain, we can begin to formulate possible paths. In our framework, we use a multi-hypothesis planner. Due to the high level of uncertainty in unstructured outdoor scenes, it's natural to formulate multiple possible paths and iteratively remove unsafe paths as more information is gathered. A traditional LiDAR-based planner will assign cost to the paths based on metrics such as distance and terrain roughness. In our problem formulation, semantic information is critical to recognize untraversable terrain. In this scenario, the shortest path is not the lowest cost. We start with a previously fused semantic point cloud. and cluster regions as safe, unsafe, or unknown based on the semantic labels and uncertainties associated with them. A RRT variant is then used to plan multiple paths to the goal. Each vertex of the RRT graph is assigned a safety score based on the semantic class probabilities of the terrain and the uncertainties associated with the Bayesian neural network measurements. To reduce uncertainty in our paths, the planner takes additional views of the environment. Due to computational costs and limited resources on a mobile robot, we optimize for the best possible new next best view measurement. To find the next best view, we'll account for the current map knowledge with partial semantic information and uncertainties, and also the proposed multiple paths planned. The goal is to maximize the reduction of uncertainty in the planned paths as we take a new measurement. Given the current viewpoint, there are a set of uncertain regions in the scene due to environmental factors, such as lighting or ambiguous surface types. To reduce the uncertainty of the paths which traverse through the uncertain regions, we move the sensor to a next best view, which can best reduce uncertainty in those uncertain regions. Our next best view objective is a function of distance, angle, visibility, and expected uncertainty reduction. We're now ready to select a safe path. However, if our budget allows, we can take additional next best view measurements to iteratively increase our confidence in our paths. If we can confirm a path is safe, or if we can confirm all paths are unsafe, then there is no need for any further measurements. A full framework iteratively reduces path uncertainty, given the number of next best views allowed, until we are able to safely navigate through the unstructured outdoor environment. Our planner is evaluated on both simulated and real-world environments and compared against a state-of-the-art baseline. These figures show results for path safety, which is the ability of our planner to avoid untraversable terrains and real-world outdoor environments over 500 trials. What you see are stacked bar graphs showing the safety performance of the baseline planners and our planner. The x-axis are the planner types. The first two are baselines, and 3 through 7 are planners with increasing amounts of next best view measurements. The y-axis is in percentage, with the green as a safe path is taken, red as an unsafe path is taken, and blue as all paths are confirmed unsafe, so no path was taken. More green and blue is better. Our planner significantly improves path safety, even with only one next best view. Semantic information is clearly critical to safety in path planning. As more measurements are taken, path safety continues to improve, but begins to plateau. The baseline results are highlighted. This planner performs poorly because the environments have flat regions which appear to be traversable, but actually have untraversable terrain types. The baseline planner does not use any semantic information, so it performs poorly. The second baseline is a comparison with a planner that has an initial measurement with semantic information, but without any next best views taken. The planner performance improves from no semantic information at all, but performance is still poor. Here are the results after only one next best view. The planner performance increases dramatically because the uncertainty of the terrain types has been greatly reduced. After one next best view measurement, the planner is able to avoid unsafe terrains with much higher probability. Here is an ablation study of the efficacy of our next best view objective function in reducing path uncertainty. Our full objective function outperforms the random baseline and objectives which only account for scene geometry or scene uncertainty. In conclusion, we have presented a novel framework for navigation through uncertain outdoor environments. Our framework reasons about semantic terrain types and uncertainties associated with ambiguous measurements. Multiple paths are planned, and we iteratively reduce path uncertainty until a safe path can be selected for all paths confirmed unsafe. Our experiment demonstrates significant improvement in path safety over baselines. We would like to acknowledge the Office of Naval Research for funding this work, and Narek Wu and Hadi Alzair for their assistance with preliminary software implementation. Thanks for watching, and make sure to read our full paper for details and results.